Hello, hello. There they are. There's the Lila. There's the Lila. There's the Tania. All right. There is the Shen, the Harris, the Jadith, the Michael, the Joyce. All right. All right. Excellent. Well said. I said Harris, Jadith. Those are all the visuals. And now I think I see in the chat. I see something. Good afternoon, Jerry. Good afternoon, Luis. Hi, how are you? I mean, I'm fine, thank you. I appreciate it, Lila. Little Fernet. What's up? Ooh, I like the what's up. Not much. What's up with you, Shen? I'm doing well, thank you, Harris. Okay, thank you. I appreciate it. Yeah, we're in a new, well, you don't want to see what's under it. Yes, we're definitely in the new chemo land of various people are giving me. Anyway, yes, thank you. I appreciate it. Okay. Wait, who else? Oh, so hello, Jadith. Good afternoon, Leah. Wait, what, am I still saying that wrong? Sorry, you might want to correct me. I'm saying Leah. I think it's Leah. No, I'm not sure. Oh, you'll tell me. All right. Tania, good. Feeling, thank you. Good. I mean, feeling good. Thank you. Oh, thank you for that comment, Raymond. Okay. And good. Everything is good. Nico. Okay. I'm sort of lying, but okay. No, so here's the deal. Here's the deal. Oh, Shen. Whoa, Shen. I see it. Oh, that's cray cray. Okay. And I hope you guys noticed too, there is a new portal open for anytime you do one of these animated um avatars, you totally can get points for that. Plus, I guess it also counts as a normal avatar, so you can double dip. Um, and good afternoon, Samaya. Samaya's phone. Okay, and everybody else that I haven't said, like Sophia, good afternoon, Abdul, good afternoon, Danielle, good afternoon. And sorry, Leah, can you tell me in the private chat or chat if it's Leah or Leah? I can't believe it's this late in the semester and I'm still asking, that I'm asking, but because I have both in my family. Um, anyway,
It, it's Leah.
it's Leah. Okay, thank you.
Yeah,
And you just got points for
you're
using your
welcome.
voice. Leah. I may get it wrong one more time, but I hope not. Leah.
That's okay. Yeah.
Thanks. Okay, Leah, because no H. Okay, got it. Thank you. All right, and thank you for using your voice. That is total points. Okay. All right, so truly appreciated. Okay. So what we have to do today, I mean, some logistics. So yes, in terms of how I'm feeling, thank you for I mean, feeling great, all that frenetic as usual, overly caffeinated as usual. Um, but indeed, it is true that this week, not to be too personal, but it is a chemo week. So just to remind you, Wednesday you'll have Professor Lou, and so you should use that as an opportunity. She has the practice exam. I mean, she's in Google Classroom, right? She has access to your practice exam. You should really use Wednesday. And of course, I'm always in communication with her. You should really use Wednesday as an opportunity to ask any questions about the practice exam that you have. And the shorter and the more concrete the questions, the more she can get to. She may do it again in her format of a board meeting or something like that. Like it's up to her, but whatever it is, Wednesday is meant to help you with the exam. So again, to remind you, of course, the exam will be posted Thursday night, no later than 8. And then you have to Monday to do it. You should be aware that sorry, I'm looking. You should be aware that I did just post something in the stream of Google Classroom that I did update the practice exam to reflect the fact that to make your final exam shorter, to be honest. That in your practice exam now, I included a copy of one of the most recent homeworks, the Doppler Effect homework, which is what I'm going to spend all of this period going over. Or helping you with. So I just want to make it clear to you by just updating a single copy of that. I mean, by adding that to your practice exam, I'm just making it clear that yes, you're responsible for that in your midterm. It'll be a very similar problem, but I'll change the numbers, whatever. Um, um, and you should check that out. Like, be clear on that. When you take your midterm, the Doppler effect is part of it. That way, it won't be part of the final exam. Um, You should also notice, I think, and I note also I did that because I made a correction. I noticed in your practice midterm, I don't know how I'd missed this before, but like the points didn't add up correctly or something. They do now. But you'll notice, like, the exam is very, very long. Your exam won't be that long, even if it looks that long, because one way or another, you're going to have choices on your exam, as I think you could tell from last year's midterm, and even from the way it's now updated. You can tell that you will have choices, but you should also be able to tell if you've already looked at the midterm and now you look at the update. I mean, if you look at the practice, and now you look at the update, you'll be able to tell that, like, what choices you have. You don't know until you get there. So, I mean, you do have to know like, in order to prepare for this, you need to know how to solve every kind of problem. But then once you get, so you could tell, like, I mean, you know what I'm about to say. Like, I might say you have to do this one, but then choose these two, or you have to do that one, but then choose this. So, like, you won't have a full reign of choices, but you will have some kind of choice, so that in the end of the day, what you're turning into me is a lot shorter than the document indicates. I hope that's clear. So just be prepared. You got to know how to do everything, but at that final analysis, you're going to be focusing your efforts on what you want to focus your efforts on to a certain extent. I'm just looking at the chat. All right, so hopefully that's clear. But that does include the Doppler effect. That's the bottom line. So that's what I want to talk about today. Oh, and then also, I hope this is clear. I can't go through every bit of that practice midterm. We just don't have time for me to walk through every single bit of it, and neither can Professor Liu. But again, if you do your job, if you put a little effort into it, I promise you that every single problem that's in your practice midterm is somewhere. There's a video where I walk through an entire solution to that problem. Probably most of the videos are the last couple of semesters, but you can find them and share with your classmates. So it's there somewhere. Okay, I keep thinking that people are adding to the chat, but they're not, just adding to the. So stop me. Okay. So what I'm about to do in a minute, if everything is sort of clear, what I'm about to do in a minute is I'm literally going to walk through my version of how to solve the Doppler effect homework that many of you made a good first stab on, but you never knew quite what I was looking for. And it's a very vaguely, badly written assignment. Like, I know that. So I'm going to walk through it now. And again, that means that once you understand this, of course, later on, you can hand in a revised version of the homework and get all the rest of the points. But that's not the main purpose. The main thing is that you understand it for the exam. So so in effect, what I'm walking through now is what is now problem 5 of your practice exam. Um, and you should stop me at any moment if there's any issues. Okay, so that said, hold on, I'm going to get a calculator 1 second. Okay. Okay. Okay, so I'm about to do the Doppler effect. I'm about to do an effect homework 4 with the numbers of homework 4 again, to the extent that this will appear. I mean, it will appear on your exam. Obviously, I'll change the numbers and maybe try to change the wording. We'll see, but maybe not. Um, so here's a situation. Well, so just raise your electronic hand if it's clear, like what's going on, what I'm about to do, where we are in the class. Like, just raise your hand if you're good for me to. Okay. Thank you, Raymond. Thank you, Shen. Thank you, Lila. Thank you, Mantra. Thank you, Montserrat. Thank you, Camille, Louis, Glees, Danielle. Okay. All right. Cool. Awesome. Thank you. All right. So here we go. All right. First of all, let me say, if I haven't said this specifically before, the condition that must be met in order for a Doppler effect to occur, like the kind of situation we have to have that allows for a Doppler effect. Oh, sorry, I'm looking at the direct chat. Got it. Okay. For there to be a Doppler effect, first of all, there has to be a wave. I mean, there has to be, and something is sending a wave to something else. The thing that's sending the wave we call the source. The thing that's getting the wave we call the receiver. Okay. Um, most common version, most commonly known version of the Doppler effect is with sound waves, but it doesn't need to be a sound wave. It could be any kind of wave. Or here we're going to picture a sound wave. But if any kind of wave is sent from a source to a receiver, if either the source or the receiver is moving relative to the wave's medium, then a Doppler effect will occur. Let me say that again as explicit. Like I'm not even pretending that I've said what a Doppler effect is. I'm just saying why there would ever be a Doppler effect is if the source or the receiver of a wave has motion, has a non-zero velocity relative to the wave's medium, then we get a Doppler effect. Okay. And strictly speaking, when I say or, it's an inclusive or. Like actually, technically, if both the source and the receiver are moving, as long as they're moving differently, there could be a Doppler effect too. But as long as at least one of either the source or the receiver is moving relative to the wave's medium, then we will get a Doppler effect. And you should please, and again, let me remind you all, if you ever write anything down that I said, but I didn't write down, you should totally screenshot that and send it and put it in the notes portal and get points for it. Like I highly encourage. So this is what, because I can't always write everything down. So again, you heard what I just said, that if the source or the receiver of a wave has velocity relative to the wave's medium, then we're going to get a Doppler effect. But let me put that one other way that's like really relevant to the analysis. What that means is if either the source or the wave is not in the same reference frame as the medium for the wave, then we get a Doppler effect. Remember, to be in the same reference frame as something means to be moving with the same speed as it, to be at rest relative to it, right? So first of all, we've got a wave. If we've got a wave, we definitely have a medium. If we have a medium, the medium has some speed. Relative to Earth, it might be one thing. Relative to a train, it might be another, blah, blah, blah. But we're now saying, okay, if you're moving through that medium, that's the condition. On the next page, I'm going to say, what is the effect? What is the Doppler effect itself? It is this. Like question, what is the Doppler effect itself? The answer is source will measure a different frequency from that measured by receiver. All right, I just want to establish, sorry, before I get into the math, mostly I want to do the math today, but the condition for the Doppler effect is that a source sends a wave to a receiver, and either the source or the receiver is not stationary relative to the medium for the wave. That's the condition. The effect is that the source and the receiver will disagree on the frequency of that wave. I mean, there's one wave being sent from a source to a receiver. If the source is not in the same reference frame as the medium, or the receiver is not in the same reference frame as the medium, then the source and the receiver will disagree on their frequency measurements for that one wave. They will get different measurements. And let's be clear, I'm talking about measurements. I'm not talking about like perceptions or optical illusions or anything like that. I'm talking about measurements, and I'm saying that the frequency of a given wave as measured by the receiver will differ from the frequency of that same given wave as measured by the source. This effect is a result of the relational character of velocity, right? It's a result of the fact that the source and the receiver are not in the same perspective, the same reference frame. And what we know about the relational character of velocities, what we know from Galileo's principle of relativity, is that the laws of physics are the same in all inertial reference frames. That is to say, as long as things are moving at a constant velocity, one constant velocity is no better or more correct than another. So what I'm just trying to say before I start doing the math is that the Doppler effect is when the source and the receiver get two different frequencies for the same wave. And if it's a true Doppler effect, both of those measurements are equally correct. It is not an illusion, it's not a misperception, and it's not an inaccuracy. It is a difference in measurement. It's a relativity, a Galilean relativity effect, where we realize that if velocities are relative to frame of reference, it turns out that wave frequencies are also relative to frame of reference. Okay, couple other quick notes on this. And again, obviously my goal is to like do it mathematically, but okay. Okay. Couple of things. So again, the Doppler effect can apply to any wave at all. Ultimately, even in the complicated, deep case of light. But for the moment now, we're going to talk about it in terms of sound. That's the most common typical scenario in which the Doppler effect plays itself out. So a couple of quick notes on sound. Sound is a wave. Okay, all the math and the graphs and the differential equations that we're saying apply to waves in general apply to sound. And one thing that we've been saying for sure is that for there to be a wave, there must be a medium, right? A wave is a bunch of material, particular, harmonic oscillators, all oscillating out of phase with one another in a very specific patterned way, right? So in order to have a pulse, you must have a bunch of things that are oscillating so as to create that pulse, right? In order to have a wiggle, you've got to have things wiggling. In the case of sound, the things wiggling are air molecules. Like, in other words, the medium, and it, generally speaking, I mean, they could be water molecules. They could be the molecules inside the string of a guitar. But generally speaking, especially like by the time the sound goes from a musical instrument or a speaker or some kind of source to a human ear, generally speaking, it has traveled through air, through a bunch of air molecules that are all wiggling. Now, sidebar, if you want to take notes on this, the truth of the matter is, in the case of sound going through air, again, it obeys all the math and all the concepts that we've been saying. It happens, just so you know, so I'm being realistic. The one way, I mean, in other words, the math works exactly the way pulses on a string, as in lab 3 or 4, or lab 3, operate. But one difference when you're visual, and all the graphs are the same, all the cosines are the same. But one thing when you're visualizing it, to be honest, and you'll notice this in websites or in textbooks, like on a string, on a long slinky, as in lab 3, at any given moment, the axis of oscillation is perpendicular to the axis of propagation. Like each little oscillator is going up and down, which creates a pulse that goes left and right in lab 3, right? So that's called so your graphs really are about like how high is the string for any given moment or at any given horizontal position. Technically, that's called a transverse wave. Trans means across. A transverse wave is when the axis of oscillation is across, is perpendicular to the axis of propagation. In the case of sound, just so that you know, that's not exactly what's happening. In fact, that's not what's happening. Air molecules, when sound goes from me across the room to you, and I'm not talking about the internet or anything, I'm just saying, like, if we were standing in the same room, or when sound goes from the speaker in your computer to the ear in your body, right? When it goes across the air, it's not that a little air molecule over here is going up and then down, and then an air molecule over here is going up and then down. It's rather that air molecules are pushing forward and backward. Air molecules are getting closer together and then spreading out. And then air molecules over here are getting closer together and then spreading out. In other words, so again, same idea, same math, cosines, all of that. But it's just that in the case of air, the air molecules are compressing and then refracting, so to speak. They're squeezing together and coming apart. So the axis of oscillation is parallel to, is the same axis as the axis of propagation. So that's not called a transverse wave anymore. That's called a compression wave, or sometimes a longitudinal wave, synonyms. So sound is, strictly speaking, a longitudinal wave or a compression wave in a medium of generally air. Okay, that's just so you can picture it. And that's why it's like drawn like wave fronts, like when you, rather than squigglies, but all the same. Okay. So when sound travels through the medium of air at standard temperature and pressure, the speed at which sound travels relative to air is approximately 340 meters per second. Now, again, this goes back to the last class or the class before. This is the thing that we can say about waves that we can't say about particles. This comes from the wave equation, the whole idea, like the whole omega over k squared term in the wave equation we found out really means v squared, where v is the phase velocity or the propagation speed of the waves. And what we found out is that v is determined fully by parameters, fully determined by the material properties of the oscillators comprising the medium for the wave. So in short, remember the one thing that we can, sorry. Oh, okay. I see in the chat. I see in the direct chat. Good. Okay. So there's a direct chat question. It's very fair. The direct chat says, what does STP stand for? Oh, yes. Correct. Exactly. Really good. But I'm going to say for everybody, totally give yourself tons of points. Like submit. You just answered your own question beautifully, but just goes to show how helpful it is to ask a question. Okay, anyway. So what a person just asked in direct chat was, what does STP stand for? And then they correctly surmised that it stands for standard temperature and pressure of air. And what does WM stand for? And I'm going to use this a lot in the mathematical analysis we're about to do. VWM stands for velocity of wave relative to medium. Now, remember now, I'm answering the first question, but they already figured that out. But I'm saying to everybody, here's my point. We're going to use that in the math of what we're about to do. I'm saying what's interesting about waves is once you specify, well, let me back up. What's interesting about velocity is always relational. This comes from physics 203 in principle. It comes from Galileo in reality. Like when you specify the velocity of something, you must be specifying it in relation to something else. Properly speaking, whenever we talk about velocities, we should always be able to put two subscripts after the V to say velocity of what compared to what. Now I'm going to say with a wave, it turns out once you specify the medium, you automatically know the speed of the wave relative to that medium. It will literally not change as long as the medium does not change because it's determined by material properties, parameters of the medium. So it turns out, for example, with sound, once you specify that the air molecules are all at a certain temperature, standard temperature, and they're at a certain pressure, we then know in advance the wave is going to travel, the sound wave will travel through through air at 340 meters per second relative to air, which then means relative to anything that's standing still in the air. The sound will travel 340 meters per second. But the fascinating thing about waves is that means if you're traveling at some other speed relative to the air, then you're not going to agree with that. And you're going to be just as correct as the air is, right? This is where the Doppler effect is going to come into play, like in a moment. I'm saying the one thing you can always know about a wave is how fast it's traveling relative to its medium. But therefore, you can also know if you are making the wave or you're receiving the wave and you are not standing still in the medium, you're going to experience a differently traveling wave. And that leads to this thing called the Doppler effect. If in the case of sound, okay, we're going to use that in a minute. In the case of sound, it's also important to know that the frequency of a sound wave is interpreted by the human brain as pitch, as in note, as in, for example, if a sound wave vibrates at 400, now please do write this down again. I will not, but you should. As an example, if a sound wave oscillates back and forth, cycles at 440 cycles per second, 440 hertz, that is what we all recognize and define as the A in the middle of a piano, middle A. Like literally, that is an example, but it's not, I'm not making that up. Like that's literally true. What it means to hear an A, what it means to hear an A is to hear sound, air molecules vibrating, oscillating at 440 cycles per second. To hear middle C on the piano is to hear 256 cycles per second. Again, that's not an arbitrary, like that's real. To hear a C one octave up from middle C is to hear 512 hertz. Like all of the, it's all mathematical in the end. And if you're thinking, wait, okay, I like music, but I don't know what he's talking about with these notes. Like I don't know what an A is or a C is. Like what is he even like? I hear notes and I don't know what they're called and I don't care. That's fine. But let's get this straight. If you listen to music at all, I mean, if you can picture a piano and you know what I'm talking about, then hopefully this means something to you. But let's say you don't play any instrument at all, but you listen to music, right? So picture your favorite song that you know really well. Whether or not you feel like you can sing it well, you know it well, right? So if you went to a karaoke bar and someone then tried to sing your favorite song, like karaoke, right? I think we both know when that unprofessional person, if they hit the wrong note at the right time or at the wrong time, right? You know it, right? When they hit the note badly, if they're go flat, as we say, or sharp, as we say, then you'd be like, oh God, I wish I were doing like what? Have another drink, Larry, like or whatever, right? You would know it if it, even if you don't think you know A or B or this or that, you know it when it's wrong. So let's say you're like, oh, you hit it too low. It's supposed to be higher than that, dude. What you're really saying is they hit a note that was lower on the piano than it should have been. And what I'm telling you is that means that their note wasn't, their air molecules were not cycling as frequently as they should have been. Like, so even if you don't know the letters, you're responding to cycles of vibration. I hope that makes so. Bottom line, the higher frequency of a pitch, excuse me, the higher frequency of a sound, the higher the note, like on a piano or on a guitar or in a vocal register or whatever. And those of you who do know how notes work and stuff, you might be interested to know that they all correspond to numbers of frequencies. Okay, now having said that, I'm still looking at chat. Let me back up and explain that the basic Doppler effect, then again, we're going to look at it with regard to sound and we're going to run the numbers. But the basic idea is like just think of it this way. It has to do with how waves always move at a given velocity relative to their medium. So the Doppler effect occurs when somebody, either the source or the receiver, is not standing still in the medium. Then the source and the receiver will disagree, it turns out, on the frequency of the wave, i.e., the note, the pitch of the sound that has been transmitted. Oh, I'm looking at the chat. Oh, what a great question. Okay, that is a perfect question. First of all, first thing I was just about to say, kind of, and second of all, for doing the math that we have to get to, that is a perfect. So, and I'm not blowing smoke. So Raymond's question, no, 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 don't about no apology zone. No, I mean, if you, it's not an interruption. First of all, it's your class, not. But second of all, it's exactly the right question. So I hope you can see in the chat. He's asking, is the wavelength of the wave always the same regardless of the scenario? So, so the answer is a subtle answer. We're going to see it play out right now. The answer is within a given scenario, the wavelength is the one thing that the source and the receiver will agree on within a scenario. And you all should write this down. You're going to see this in a minute, but this is super important. Within a given Doppler case scenario, the source and the receiver will agree on one thing, and that is the wavelength of the sound. From scenario to scenario, the wavelength can and will change. It's not the same across scenarios, but within a scenario, it is the same across frames of reference. The technical word for what and I'll explain that more in a minute, like I'll show you, but that's super like a good thing to start with. The technical word for what wavelength is, wavelength in terms of Doppler effect, wavelength is invariant. Invariant. That's kind of like saying constant, but it's deeper and more specific than that. Invariant means unchanging. And whenever in physics we say something is invariant, 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 one word. When we say that a quantity is invariant, what that means is it doesn't matter what frame of reference you're in. It doesn't matter how fast you're moving. You'll still observe that quantity to be the same. Now, a lot of things are not like that in physics, but some are. And wavelength is an example. Let me give you an, okay, but it won't be the same from scenario to scenario, from case to case. Let me tell you right now, again, in general terms, and then I'm going to get to the numbers, but such a great question. So look, here's the Doppler effect in general. Just for a minute, forget sound. Well, Yeah, forget sound for a minute. Just imagine that you're at Coney Island or Far Rockaway Beach, like you're at the beach, and there's like water, right? And so some barge or something is way out there creating waves. Like something is sitting out there in the water or is out there in the water and is making waves come in to you. Like it might even be that the moon is like generating gravitational tidal forces and that, but whatever it is, something is causing waves to come into you toward you. Now, let's say it's generating waves that have a frequency of 1 hertz, i.e., there's one wave that crashes on the ocean that breaks on the sand every 1 second, just to make the number simple, right? So let's say the frequency according to the source is 1 hertz. Well, if you're standing on the beach, if you're literally standing, if you are stationary relative to the water, and the thing making the waves was stationary relative to the water, so it generates these waves at 1 cycle per every second. Well, if you're just standing there, then okay, you're going to receive a wave every second. Like no Doppler effect if nothing is moving. But if you, the receiver of the waves, are not in the same frame of reference of the water, say, in other words, you start running in toward the water, right? So now you have velocity relative to the water itself. Then I hope you can all see 2 things. If you start running in toward the water, number one, Raymond is correct. Like, even though you're running into the water now and something is going to change, if each one of these waves is like a meter apart according to the ship that's making them, or according to the moon that's making them, or whatever, if each one or according to the water, whatever you're doing, if you measure these waves and you see that each crest is 1 meter away from the next crest, then even if you're running in, I mean, you're running in with a meter stick, there's nothing you could do. Those waves are still each 1 meter apart. So on the one hand, this is what Raymond is like raising as an issue. The wavelength is going to be agreed upon by the ship and the water and you, even if you're moving in some funny way compared to the ship or the water, right? Wavelength, in other words, as he's saying or implying, is invariant. The wavelength you'll both agree on. The source and the receiver and the medium will all agree on the wavelength. However, if that's true, what happens is now a Doppler effect because you're running in toward the waves. And you could just imagine, just qualitatively, just picture it. All the waves are still a meter apart from each other, even though you're running in toward them. But the thing is, they've been generated, they're coming out from the ship one every second. So one comes out, and then a second later, the next one come out. But during that second, you're running in toward the wave, right? So it's a meter away, but you're running toward it. I mean, the next wave crest is a meter away, but you're running toward it. So you're cutting down on the amount of time that you'd have to wait to hit the next wave front. So what will happen is, even though the wavelengths everybody agrees on, first of all, you're not going to agree. Say these waves are coming in 100 meters per second, like each wave crest is traveling at 100 meters per second relative to the water, relative to the ship that made them. If you're running now, you're not going to observe them coming in 100 meters per second. They're coming at you a lot faster. If you're running at 10 meters per second toward a wave that's coming in at 100 meters per second, from your perspective, it's coming in at 110 meters per second, right? And we'll do the math on that in a second. But right, and furthermore, more importantly, that therefore, that means even though you still have the next wave front is a meter away, you're cutting down, you're running toward it at 110, or I mean, it's coming into you at 110 rather than 100. So it's going to take less time, less than a second before it gets to you. So the net effect, even if you all of those numbers just fogged through your brain, I think you can all join with me in imagining if you're running toward wave fronts at the beach, you're going to hit them more frequently than they were sent out. And nobody's incorrect. It's not an illusion. The frequency that you measure as a receiver will be higher than the frequency as measured by the source if you were running toward them. If you were running away, same logic in reverse. It's going to take more time to get to each next wave front than otherwise. So because the wavelength, everybody agrees, I'm saying the wavelength, everybody would agree in each of those scenarios, but everybody would disagree. The source and the receiver would disagree on the velocity, the speed, and therefore they will disagree. If the wavelength is held constant and they disagree on V, they will disagree on frequency, and they'll both be right. The source frequency measurement will be one number, the received frequency measurement will be a different number, and they'll both be correct. But that's the Doppler effect. When you apply it to sound, what you get, and I will come do the math in a minute. I know I keep saying that, but it's true, sort of. When you apply it to sound, the common experience of the Doppler effect, like in New York City, is like, what was that? Like, what am I doing? I'm not talking about a siren. I mean, siren's even more exaggerated. I'm saying if someone is on a motorcycle or in a car and they're just blaring their horn, they're just pressing their horn, which makes a constant frequency, one note, right? So someone's jamming on their horn, and I don't have perfect pitch, but let's say like they're making a note like middle C or whatever. They hear middle C. If they had a tape recorder or an iPhone in their car, they would record middle C, let's say 256 hertz, let's say. But now if they're coming toward you, this would be like the boat that's making the waves coming in toward, or let's even, sorry, I don't want to complicate things. Let's say you're running toward them. I mean, either way it works. That's what we're going to see the numbers in a minute. But let's say, to keep the analogy that I just made with the ocean, if you're running toward, if you're running toward that horn, the person at rest with respect to the horn will measure 256 hertz. They'll hear a C. But if you're running in toward it, you're both going to agree on the wavelength of that sound, but you're not going to agree on the speed of that sound. And therefore, you're not going to agree on the frequency of that sound. If you're running in toward the source of the sound, the wave fronts will hit your ear more frequently. You'll hear a higher frequency sound, which means you'll hear a higher note. If they're playing C, you might hear C sharp, if that means, or D, if that means anything to you. And then when you pass them and you're running away from them, now the opposite effect will occur. I mean, the same logic, but in the reverse direction. So now you'll hear a lower note than they're hearing. So the whole time they hear one note, but if you're running toward them, you hear a higher one. If you run away from them, you're hearing a low one. And it turns out the same logic, but not necessarily the same numbers. The same logic applies if they're coming toward you and then go away from you. So if they're coming toward you, you'll hear something higher than they hear. And then when they're going away from you, you'll hear something lower than they hear. So when they pass you, you hear, right? Last thing I'm going to say about this qualitatively, what I'm saying qualitatively, I'm saying in a Doppler effect, the receiver and the source are not in the same frame of reference as each other. That's the condition. The effect is that the receiver and source will measure two different speeds of the wave. The speed of the wave is always the same thing relative to the medium, but either the source or the receiver is not in the same frame of reference as the medium. So the source and the receiver will measure two different speeds of the wave. And therefore, since the wavelength is constant, is invariant, is agreed upon by both of them, they'll measure two different frequencies of the wave. Speed is already interesting, but people don't walk around with speedometers in the middle of New York City usually when they're hearing sounds. But frequency, we just automatically interpret as pitch. So we notice that right away. So the Doppler effect is that two different speeds two different frames of reference on a given wave lead to two different frequencies, which in the case of sound means two different notes, two different sounds, two different pitches. And that's what we want to now study numerically. I hope that made any sense. And maybe Raven could tell me privately or publicly if that, I mean, that was a long, but most of that was what I was going to say anyway, obviously. But the bottom line is yes. Okay, great. Thank you. Totally appreciate it. Totally appreciate it. So what that means is when I'm going to turn and run the numbers of the homework problem, the homework assignment, my whole approach to it is going to be in every scenario to first solve for the wavelength. Like literally, that's my problem solving approach, is to first solve for the wavelength, because that's the one thing I can rely on the source and the receiver to agree on. And from that, then I'll do the rest. So okay, so let's go to the homework problem. Well, okay. So what's given qualitatively is like everything I just said, that we have two different frames of reference on the same wave. What's generally then given is a bunch of numbers. But then with the Doppler effect, you're given these numbers and then you're asked. So okay, so you're given a bunch of numbers. In the case of the homework, here, I'm going to redraw this diagram so we can expand on it. So oh, I'm sorry, and in homework 4, I think homework is a total, yeah, oh no, it is sound. It is sound. Yeah, okay. So homework 4, we're talking about a sound wave. So this ridiculous, like these ridiculous icons or whatever that I'm drawing, like I mean the left thing, this is supposed to be a wave source. In other words, it's meant in the case of sound to be like a speaker, right? And then this is supposed to be an ear, like a wave receiver. Okay. So there have to be both for there to be a wave at all and for there to be a Doppler effect. Then what's given, so everything on this page is like the givens, okay? What else is given would be the velocity of the wave relative to the medium. That would be given because that's what we can know about a wave in advance before we even set up any kind of specific scenario. So what's given in this case is we're talking about sound. So, and we're talking about it in air, apparently. So the sound is travels at 340 meters per second relative to the medium. In fact, let me be more specific. Let me just say here. So like we're going to say let W stand for wave, M stands for medium, S stands for source, R stands for receiver. And if this is all in terms of sound, then wave by wave, we mean sound. By medium, we mean air at STP. Source, we mean like a speaker or voice. So, and then receiver, we mean like an ear. Okay, just so you can follow what I'm talking about. So what else is given in a Doppler effect? What else would be given is like the frequency of the wave as measured by the source, right? In other words, the note that the person who has the speaker would experience. In this case, it's given as 800 hertz. Now that's like, in other words, that's basically like an A flat, but not middle A, if you care. Like, in other words, middle A on a piano is like 440 hertz. So an octave up is like 880 hertz. And so if you go a little lower than that, 800, you're like in an A flat or maybe even a G, but one octave up from the middle, if you care, whatever. But I'm just saying these are real numbers. These are realistic pieces of information. So now one other thing. So here in this case, oh my God, I don't even know why Feeble-Fetzer and Weeble-Fetzer were spelled two different ways. That's a mistake. I apologize. I'll fix that in the test. I never even noticed that before. That's not meant to be. That's a mistake. But can I fix it right now? I can't fix it right now without rabbit holing. But so you notice, in other words, one other number is given to you, and it's 80 in the homework. I'll screen share just so you can see what I'm talking about. Sorry. Right. So I'm talking about this Just to be clear, of course, this was your homework. And again, this is now stapled to the back of your practice exam, blah, 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 blah. But there's one other number given in this sort of vaguely expressed problem. And that number is the 80 right in the middle of the page right now. Like, what is that? Okay, what that is the motion of either the receiver or the source relative to the medium. And the reason it's sort of given vague, like, well, why it says it's not clearly recorded which device moved, blah, blah, blah. The direction is also unclear. The reason is because I'm trying to keep this open-ended, because what I want you to see by the end of this class and for your exam is there's 4 standard possibilities. There's 4 basic cases or scenarios, like Raymond said. There's 4 different ways the Doppler effect could take place, basically. You could have a receiver up. Well, so I'm going to write this. So I'm going to switch the screen back. Pardon me. But again, this is the problem we're doing. If you, for the purpose of the recording or whatever, this is the problem. In fact, I'll even say, let's check this out. Sorry, as long as I'm doing this, trying to be as helpful as possible. Notice at the end of your practice midterm, this problem is now stapled in. But notice by the end, what it's saying is, what we got to do with these numbers is we've got to figure out the received frequency, the frequency as measured by the receiver for each of the 4 possible cases. And then the point of it all is to compare and contrast the numbers that we get for the 4 possible scenarios and see what that implies about the medium for a wave. So, I mean, I'm going to switch the screens again, but what do I mean by the 4 cases? What I mean by the 4 cases is the receiver could approach the source, or the receiver could recede, go back from the source, or the source could go in toward the receiver, or the source could go away from the receiver. Those are the 4 basic cases, right? Now, the one, and we're going to analyze the number. In each case, we know the frequency as measured by the source. What we got to find out is the frequency as measured by the receiver. It's going to be different because it's a Doppler effect. That's the whole point. So it's all about comparing what note was heard versus what note was sent. I mean, what note was received versus what note was sent, so to speak. Let me just switch the screen share. Okay, so back to okay. So I'm going to put that 80 number in a moment, but let me just make clear first. By 4 cases, I mean, and I usually do them in this order. You know, it doesn't matter what number I call which, but I tend to do them in this order. Oh, sorry. Okay, those are the 4 possible approaches. And what I'm saying is that number 80 that we're about to use, the number 80, like, either is the velocity of the receiver relative to the medium, or it's the velocity of the source relative to the medium, depending on which case we're talking about. And we either make it a positive number or we make it a negative number, depending on which case we're talking about. Hopefully you follow that. So in order to make the decision about positives and negatives, before I go any further, I would say, if this is the given, right, that we have a source over here, we know the frequency as measured by it, we know the speed of the wave as measured by the medium, and we're ultimately, like, the ultimate question is, what is the frequency of the wave as measured by the receiver, right? If that's our ultimate question, and we want to know it for each of the 4 cases, right? Then what I want to say, the first thing I do in every Doppler effect problem for all the cases right away is I set up and I say, whichever direction the wave is traveling, from source to receiver, I call that positive. That is a choice that I am making. You could make a different choice, but don't. I mean, like, in other words, God didn't make that choice. I'm making that choice, but it is the strategic choice to make. Again, this is all about Galileo. It's all about choosing your frame of reference. All frames of reference are equally correct, but some are a heck of a lot more convenient than others. And you have to choose a frame of reference. You can't not choose. It's not like tomorrow. Well, it is like tomorrow where you have to choose. Anyway, you have to choose a frame of reference. So if you're listening, if you're still with me with all of my babbling, pro tip, when you do a Doppler effect problem, the first thing you should do is just a step. Like, I don't care left to right, north to south. I'm saying whichever direction the wave is moving from source to receiver, call that positive. Then analyze case by case. So to be clear, I'm going to analyze them now. Now I'm going to show you how to do it, a method that works for all the cases. Am I literally going to walk you through every single case in the next 18 minutes? No, but I'm going to walk you through enough that you can get all the cases by the time we're done with 18 minutes. So the first thing I want to say is if the receiver is approaching, then that means if the receiver is approaching, but the source is sitting still in the medium, right? Then that means that the velocity of the source relative to the medium is 0, but the velocity of the receiver relative to the medium, like in this case, if the receiver is approaching the source, it's going in toward the source, right, against the direction of the wave, that means that I would make VRM to be negative 80. Stop me if that's not clear, but that's based on my choice of calling the wave speed, the wave velocity direction positive. Therefore, if the receiver is approaching, it's going into the wave, against the wave. That's negative. Similarly, if the receiver is receding, then the velocity of the source relative to the medium is 0. The velocity of the receiver relative to the medium is positive 80, right? And if the source is approaching, okay, then now the source is moving. So the velocity of the source relative to the medium would be moving, approaching the receiver. That means going in the same direction as the wave, right? Don't memorize this, just follow the logic. My whole point of this whole thing is once you get the logic, you should get the logic and you shouldn't have to memorize anything. The VSM is positive 80 in this case, what we're calling case number 3. And the source receding, VRM would be 0 and VSM would be negative 80. So now I've established all the givens. Like the givens, in other words, are slightly different for each of the 4 cases. Now I'm going to analyze. Okay, stop me if that's not good. So let's solve for case 1. What we're going to use a method that if you follow it carefully, if you really understand and do what I'm doing, it'll be the exact same method for all the 4 cases. And you should do it to practice you do the exact same method for all the 4 cases, even if I don't finish all of them, which I won't today. Exact same method, but if you're doing it right, you will see, I'll tell you right now, spoiler alert, you'll see that you'll get a different number for every single case. It's not like you'll get, like, no 2 numbers will be the same, even though you'll do the exact same method if you do it right. Okay, so, but here's the method. Use a method that applies identically to all 4 cases. Here's the method. And it's not plug into that equation from the interweb. I've already given you a speech about that last week. If you don't remember the speech, you weren't here. Whatever that equation is, that's a fraction with v plus or minus in the top and v plus. Don't do it. Just follow what I'm about to do right now. So we're going to do case 1 here. So here's the method. Okay. And everything I'm about to do right now, this is all, if you're doing this on an exam, to be super clear, say there's a Doppler effect problem on your exam and you have to solve it. You're doing the 5-step method as always, right? Step 1, step 2, diagram, blah, step 2, step 3. What are the GDPs? I'll show you in a second. But then what I'm now calling like a method for Doppler effect is like a 3 mini step thing, 3 sub step thing that is all the expansion of the work that you would normally do in step 4. I hope that makes sense. This is all like a zooming into step 4 of the general step method. Okay. Okay, to back up, what are the step 3? What is step 3 for any, what's the GDP for any Doppler effect? It's what was written on the board last week. I'm getting myself bogged down. I'm looking at the time. The GDPs are one that for any wave, velocity equals wavelength times frequency, and the velocity of a wave relative to its medium is always constant. And step 2 is GPR form number 4, which I said at the end of like look at the video from last lecture. It's the 3 case thing. You'll see it in action in a minute, but those are the 2 GDPs. Now we apply in step 4 to the particular case. Here we go. Sub step A, like the first thing you do for any Doppler effect problem is solve for wavelength according to source. In other words, solve for the wavelength of the wave according to the source. Always do that first, no matter what case it is. How do you do that? You say wavelength, well, velocity of wave equals wavelength times frequency. Specifically, if we're using relativity, velocity of wave relative to source, because we're looking at the source right now, equals wavelength of wave according to source times frequency of wave according to source, right? Therefore, wavelength of wave according to source equals velocity of wave according to source over frequency of wave according to source. Yes, I'm going a little fast, but stop me. But I think hopefully it's clear. Wavelength, I'm just saying wavelength equals velocity over frequency, and in any given one frame of reference at a time. So I go to the next page. I'll just copy that. So this is also, so velocity of wave, sorry. Wavelength of wave according to source equals velocity of wave according to source over frequency of wave according to source. Now, do I know the velocity of the wavelength according to the source? Well, explicitly, I don't. Explicitly, I don't. I was never told that. I was told the velocity of the wave according to the medium. Right. Now, you might think they're very similar, and in this case, you're correct. I'm not trying to trick you. But specifically, you were never told and I don't know what the speaker is experiencing. I know what the air is experiencing by nature of the wave. So how could I get from one to the other? This is where GPR form number 4 comes in. Again, consult the notes from last week to see this. Specifically, case 3. Specifically, I'm saying the velocity of the wave according to the source, I can get it by adding together the velocity of the wave according to the medium plus the medium according to the source. Now, you might have to think about that, but do think about it. And in other words, VAC equals VAB plus VBC, no matter what A, B, and C are. So I just substituted W and S and M for A, B, and C. I'm trying not to get, I'm saying velocities add this way, according to relative, right? The velocity of me relative to the subway plus the velocity of the subway relative to Manhattan equals the velocity of me relative to Manhattan. That's why I take subways, because I can stand still or sit still relative to the subway. And as long as the subway is going 80 miles an hour relative to Manhattan, then I'm going 80 miles an hour relative to Manhattan without doing anything. Yes? But this works even with minus signs and even with non-zero numbers. Velocities add that way when you arrange their frames of reference in that sequence. So if I want the velocity of the wave according to the source, it equals the velocity of the wave according to the medium, which I know, plus the velocity of the medium according to the source. Now, what's the velocity of the medium according to the source? Well, I don't know that, but I do know case 2, sorry, note case 2. The velocity of the wave according to the the velocity of the medium according to the source necessarily equals the negative of the velocity of the source relative to the medium. Now, all of this, by the way, it may look like I'm making things more complicated than I need to. In a way, yes, but no. I'm giving you a method that will work for every single case, even when the numbers aren't as, just trust me. This is, if you literally follow what I'm doing and apply it to every single case, it'll work in every single case. And you'll know you did it right if you get different answers for the different cases. In fact, I'm going to say what you should get whenever the frequency is whenever the receiver is approaching or the source is approaching, when they're getting closer together, the received frequency should be higher than the source frequency, just like the Coney Island example. And whenever they're going apart, the received frequency should be lower than the source frequency. It's just that if you do this right, so you should see that as a check when you get your numbers, but the numbers will not be the same from one case to the next. Anyway, I'll go back to, so VMS equals V negative VSM. What's VSM? That was given in case number 1. VSM is 0. The source is not moving relative to the medium. So VMS equals the opposite of 0, which is just 0. Yes, it looks like I'm hitting an ant with a sledgehammer, but I'm saying this all together. I'm saying thus. VMS equals 0. So VWS, which we said VWM plus VMS equals BWS equals what you would have expected if I weren't talking so much, right? I'm saying the source is just sitting there in the air. So the source totally agrees with the air. The source is like, yeah, the sound is leaving me at 340 meters per second because it's going in the air like that. And I'm just sitting in the air. So yes, I just did a bunch of math to show you the steps to confirm what you probably already guessed or assumed, which is that according to the source, nothing funny is happening to the speed of the wave. But now here, therefore, the wavelength, which is my goal in all of this right now, is that number over the frequency according to the source. In other words, 340 meters per second over 440, oh, sorry, not 400, I mean 800, whatever was given in this problem, 800 hertz. So the wavelength is exactly 0.425 meters. Now, so what? And we only have 5 minutes left, and I'm aware of that. Again, I'm going to do this one case, and then I'm going to tell you hints for the other cases. I mean, but you do them exact. It's good practice. You do them exact same way, and or you can ask Susan, Professor Lou, on Wednesday. So this is the end of. So why did I just do this? Because I just got the wavelength according to the source. But thanks to Raymond's point, Raymond's observation, sub step B, now that was sub step A, sub of step 4 of the problem solving method. Sub step B is necessarily the wavelength of the receiver must be the same as the wavelength according to the source. That's key, Raymond's point. So necessarily VWR must be 0.425 meters. It's the one thing that both the source and the receiver will agree on is the wavelength of the wave. So therefore, so my step there is like nothing. I'm just saying, oh, so I calculated at the source first. I used V equals lambda F at the source where I knew V and I knew F. So I got lambda. Now I go over to to the last step and I say, use this lambda of wave relative to receiver and V of wave according to receiver to compute the frequency according to the receiver. In other words, so I'm going to do this. And I'm going to literally, if you're really following me, you'll see I've done all the hard work already. That's why I spent all this time. I only have 4 minutes, but I'm literally going to do the same type of computation again now. Only I'm going to do it from the receiver's perspective to get the received frequency. In the receiver's perspective, velocity of the wave relative to receiver must equal wavelength of the wave according to receiver times frequency of wave according to receiver. What am I solving for this time? F. So F of wave according to receiver must be velocity of wave according to receiver over lambda according to receiver. But now, all that work I did a second ago that seemed overkill is now not overkill, because VWR, like, what is that? What is the velocity of the wave relative to the receiver? That is not explicitly given. What's explicitly given is the velocity of the wave relative to the medium, right? VWR must be VWM plus VMR. I'm doing the same thing I did a minute ago, only now it's really like I set up the pattern then. Now there aren't going to be zeros. Like, what is VMR? I don't know that, but it ain't zero. What I know is I was given VRM. I was given that the receiver is moving through the air at a negative 80 meters per second. That means that the air is moving past the receiver at positive 80 meters per second. You see where I'm going with this? Like, next page. In other words, like I was given, look at the givens, VRM was negative 80 meters per second. Therefore, VMR, the rate at which the medium, the air, is traveling compared to the receiver, it's going 80 meters per second in the same direction as the wave, right? Equals negative of negative 80 meters per second. So VMR equals 80 meters per second. Therefore, VWR, the velocity of the wave relative to the receiver, equals VWM plus VMR. In other words, equals 340 meters per second plus 80 meters per second. What that means, and this is why the Doppler effect is happening, VWR is like 420 meters per second. I'm saying, if you back up, we have 1 more minute. If you're running into the speaker, you see the sound, you observe the sound coming into you a lot faster than if you're standing still. How much faster? 80 faster, 420. So what? So that means the frequency of the wave as measured by the receiver is the velocity of the wave measured by the receiver, which is no longer 340 over that wavelength that everybody agrees on of 0.425. So it's 420 meters per second over 0.425 meters, which equals a number that it definitely is going to be higher than 800. It is, and then we're done, obviously, but I'll see. Yeah, like 988 hertz, a lot higher than 800. Now, look, there's 1 more minute. Really quickly, I'm saying for the other 3 cases, you do the exact same method, but you will find, if you're paying attention, I know we're just about to, you'll find that in case 3, a number higher than 800, but not the same as 988. And in the other 2 cases, 2 and 4, you'll get 2 numbers that are lower than 800, but not the same as each other. You do the exact same thing, but what you'll notice, well, you'll do the same method every time is use velocity and frequency to get wavelength at source, then say that wavelength must be the same as the receiver. Then at receiver, use wavelength and velocity to get frequency at receiver. It almost seems like you're going in circles doing the same thing twice, but you're not, because the key is that the receiver and the source disagree on velocities. Therefore, they will disagree on frequency since they agree on wavelengths. That's the bottom line of that. So do the other cases and see that you get different numbers. You have it. I'll stay for a minute and answer any questions or anything. But other than that, have a nice night. And I hope that's helpful. And I'll see you next week. But Susan Liu will see you on Wednesday. Okay. But I'm still here. I'm just stopping the recording. Thank you all very much.